Good afternoon, everyone. Welcome to the robotics seminar. Today, it's a pleasure to have with us Kevin Chen. Kevin did his bachelor's from Cornell. Then he decided to go on the other side of Cambridge. And then he finally decided to come on the right side. So he joined MIT, a couple of years back. He has been working a lot on micro robotics, aerial robotics. His work has won, multiple best paper awards, and he has also won, teaching awards. And it's this space of robots at a scale which is very different from what we have seen in the seminar so far. So very excited to have Kevin with us. Kevin, please take it away.
Great. Thank you so much for a nice introduction. Okay. Let me get started. So I want to talk about agile and robust micro-aerial robot powered by soft artificial muscles. If you look at the title, there are two keywords in there, being micro and soft. I want to spend the first 10 minutes or so explaining to you what are micro-robots, and then I want to focus on a new class of micro-robots that are powered by soft artificial muscles. So first, when most people think about robots, we think about large-scale robots, like legged robots, or humanoid robots, or trains or airplanes. They span the scale of meters to the scale of hundreds of meters. On the other end of the spectrum, you can think about very tiny robots made of the MEMS technology, and they usually range from tens of microns to hundreds of microns. What I want to talk about today is insect-scale robots, and specifically, they range from 1 to 5 centimeters, and they weigh from 10 milligrams to 10 grams. As a very quick example, when I was a graduate student at Harvard, we worked on a project called the RoboBee. And the goal of the project was to create something that has similar size and functions as bees in nature. So very quickly, I want to address several questions together. The first question is, why do we study microrobots? To me, there are two answers. The first one is, by leveraging interesting physics at the centimeter scale, we can enable new functions in this robot. In this case, by leveraging flow similarity, we show the same robot was able to both fly and swim using the same actuators and wings. And more than that, we can use micro-scale robot as a platform to investigate interesting physics at the centimeter scale. By looking at the flow field that's generated by a flapping wing robot, we can infer about the lift and drag generation mechanism of flying insects. Now, the second question I want to answer is, what makes micro-robot unique compared to larger-scale robots? The short answer is that inertia become a lot less important, whereas surface effect become a lot more important. As a consequence, you can drop a legged robot from very high above and see very small amount of changes to its performance. And more than that, my colleagues have shown that micro-robot can jump off the surface of water, something that's very challenging, if not impossible, for larger scale robots. The next question I want to address is, what are potential applications of micro-robot? Well, in the short term, I can think about a lot of them. For example, I can put a camera on top of a legged robot and try to teach this legged robot to climb inside of a turbine engine and look for cracks. In the longer term, I'm envisioning using a large number of micro-scale robots and really apply them into complex situations. Now, this vision is fairly far-fetched. There's a lot of things that we cannot do right now. So I'll come back to the major challenges toward the end of this talk. What I want to do today is to tell you 3 examples of micro-scale robots. The first theme relates to the fact that micro-scale robots, although being tiny, can do multiple things in multiple environments that are sometimes challenging for larger-scale robots. And then I will spend most of my time today focusing on a third project, which is a new class of micro-robot we have created in MIT, which are micro-robots powered by soft artificial muscles. So first, let's start talking about flying robots. If I want to make a flapping wing robot that can fly, I first look into nature for inspiration. So if you imagine my arm as the leading edge of the wing stroke motion is actively controlled by an actuator, whereas the wing pitch rotation is passively mediated by a compliant flexure. So this is really a quite complex system that requires us to study the fluid structure interaction. We have set up a physical setup that allows us to capture hundreds or thousands of flapping wing videos. And not only can we capture the flapping wing kinematics, we can also measure the associated fluid flow. In this case, by looking at the particle image velocimetry experiment, we can measure the flow field and the corresponding vorticity field. By looking at the growth and shedding of leading edge vortices, we can develop a lot of intuition about how efficient our flapping wing motion is. And in addition to creating at-scale experiments, we also develop our own numerical solvers for simulating flapping wing flight. In this case, we are showing you the pressure profile on the wing surface and the isovorticity contour, again, allow us to infer about the efficiency of the flapping wing system. With this suite of numerical tools and experimental tools, we are ready to ask interesting questions. For example, the question we want to ask is, is there any similarities between flapping in water versus flapping in air? And if there is similarity, what interesting robotics functions can we enable? So we proposed a project. We want the same robot to be able to fly, to swim, and also making transitions from air to water and from water back into air. To solve this challenge, we first look into nature for inspiration. Puffins are quite amazing animals. They can fly, and they can take a dive into water. Once they're under the water, they will change their flapping frequency so they can swim around and chase for prey. Using a similar idea, we created a new robot with new wings for added lift, buoyant outriggers for maintaining stability on the water surface, and more interestingly, a gas collection chamber for impulsive takeoff. So I don't want to spend a lot of time focusing on this project, so let me just show you what this robot can do. If I start this robot on submerged in water, it will flap its wings at a relatively low frequency on the order of 10 Hertz, and it will reach the air-water interface. Once it reaches the water surface, we will turn off the wing and turn on a parallel plate. What the parallel plate does is that it will convert water into a mixture of hydrogen and oxygen, and the buoyancy force will slowly push the robot wings and fragile structures out of the water surface. And more than that, now the combination of gases can be used as fuels, and we're going to ignite them so that we can generate a huge force to break the water surface. So I recommend you to pay attention to this video. Right? We ignite, and then this combustion completes within 1/1000th of a second, impossibly generating a large enough force to break the water surface, which allows the robot to transition back into air. Now, at this moment, the robot cannot fly immediately after this just because of all the water that's on the robot. Has to wait for about 15 minutes for it to dry, and then it can fly again. So in summary, we have created a 175 milligram robot that can do multiple things, including flying, swimming, transitioning from air to water, and impossibly transition from water back into air. So this is one demonstration of how a tiny robot can do multiple things, and some of those tasks can even be challenging for larger scale robots. Following the same thread of thought, now I want to introduce another project in which we started to think about multimodal locomotion in legged robot. If I think about the previous project, right, we used combustion to overcome a surface tension forces that's over 10 times the weight of the robot. Because at the very tiny scale, surface tension is much, much larger than the weight or the forces that the robot can generate. On the other end of the spectrum, as humans, we barely feel surface tension at all. And that's because our weight is more than 1,000 times that of the surface tension that we feel. Well, if you create a slightly heavier robot that's on the order of a gram, and if its contact length is on the order of 10 centimeters, then surface tension forces and the robot weight are on the same order. Now, if you can manipulate the surface tension forces, you can really start to do something interesting. So again, we return to a question in physics, which is how do we control the magnitude of surface tension forces? And if we can control surface tension, what additional locomotive capabilities can we enable? So we came up with a new project in the sense that we want the same robot to be able to work on land, on the surface of water, controllably transition into water when it wants to, and eventually return back onto land. What's really challenging in this case is that sometimes it has to generate forces less than water surface tension, sometimes has to reduce the surface tension so it can sink. And again, without going into the details of implementation, let me just say that we used a physical phenomenon, electrowetting, which allow us to modulate the contact angle and therefore allow us to change the surface tension forces. So let me show you a demonstration. So this robot starts on land, transition onto the water surface, and it will swim to a targeted site. Once it swims to this site, we will turn on the parallel plate, and then the electrowetting footpad will sink the robot underwater. Okay, so now the robot is completely submerged, and then it will climb this incline to return back onto land. So in this very short demonstration, there are many things that are happening. The robot is leveraging interesting physics to control surface tension forces. Therefore, it can either walk on the surface of water or transition underwater. And the process of transitioning back on land also requires the robot to fight against a surface tension force that's larger than its own weight. So until recently, we are thinking about continuing to extend the locomotive capability of this robot. And specifically, we want this robot to be able to climb on walls and ceilings. And in MIT, we simply put a compliant Kapton footpad or pad on the belly of this robot. And again, we leverage a combination of capillary effect and adhesion forces. If we put a very thin water film in between the interface and the adhesion pad, there's a large adhesion force that maintains the robot on a surface, but the lubrication force allows the robot to slide along the surface. As a consequence, climbing becomes passively stable. So you don't really need a lot of sensing and feedback control. The robot can just operate as if it's just walking on land, and it can sort of walk inverted on a surface. So in summary, in the first two projects, I've shown you two examples of microrobot that can leverage interesting physics to do interesting functions. And some of those functions, I would argue, are unique compared to larger scale robots. Now, I want to change gear and spend most of my talk today explaining to you a class of new soft actuated microrobot we are focusing on MIT. First, I want to zoom out a little bit and say that our longer term vision is to create a swarm of ubiquitous and multifunctional microrobot that can operate in realistic environment. So far, the examples that I've shown you have shown you that microrobot can operate at high frequencies, and they're very precise. My colleagues in this field are solving key problems in sensing, control, and power autonomy, but I want to argue there are key questions that we are missing. Specifically, unlike insects that can work in a swarm or can interact with a dedicated environment, microrobots are fragile. You have to be very careful about tethering them so they don't collide with obstacles. And in addition, it's very hard to make a lot of them effectively. So how do we solve this key challenge in microrobotics? Well, I propose we look into another field, which is called soft robotics. For a very long time, people know how to make soft robots cheaply. And more than that, soft robots have very large range of motion. We have new sensing and control methods for soft robots. And in addition to using a battery, soft robot can also be powered by pneumatic or chemical sources. But soft robots also face their own challenges. Specifically, most soft actuators are slow, and they're not as precise as rigid actuators. And as a consequence, the functionality of most soft robots are limited compared to the state-of-the-art rigid robots. So how do we address challenges in both fields? Well, we propose to look into a new direction, what we call hybrid soft-rigid microrobot. Specifically, we envision that future microrobot will be powered by soft artificial muscles that have very high power density, while they have rigid appendages for effectively interacting with the environment. So I want to show you an example of robot that we are focusing today in MIT, which is a flying robot powered by a soft artificial muscle. I want to convince you of several things. I want to show you that this soft artificial muscle can operate at hundreds of hertz, much, much faster than existing soft actuators. I want to also show you that this robot still have very precise rigid components, such as transmissions and linkages, so we can control them with high precision. And more than that, because we are combining soft and rigid, hopefully I can convince you we can enable interesting, unique functions, such as sensing collisions or recovering from collisions. On a higher level, this soft robot consists of both rigid and soft parts. It has rigid airframes, precise rigid transmissions and linkages, What's quite unique is that the central part of this robot is powered by a dielectric elastomer actuator, which is soft in nature. Our research is motivated by the desire to address key challenges. So I want to answer 3 key questions. First, I want to convince you that soft robot can fly. And if I show you that, I can also show you why we are making a new class of aerial robot. Hopefully, I can demonstrate new functions in those soft robots. And finally, I also want to tell you about our longer-term vision about where we want to take this micro robot to. First, let me convince you that soft robot can indeed fly. I have the experience of playing with rigid actuator for many years. And specifically, I struggled with piezoelectric actuator for very long. Piezoelectric actuators are great in the sense that they are very high frequency and very precise. However, they have very tiny strain, which means assembling them into a micro robot takes a lot of training. And even worse, when a flapping wing robot is driven by a piezoelectric actuator, you have to be very careful about operating the robot. You don't want the wing to hit into an obstacle, because otherwise the impact caused by the wing can be transmitted to the actuator, which may cause the actuator to crack. So here in MIT, we developed a novel soft actuator. I want to show you that this dielectric elastomer actuator can operate at equally high frequency range on the order of 500 Hertz, while it has very large strain on the order of 10%. And because it's intrinsically soft, now we can install this actuator much more easily into micro-scale robot, and we can make a lot of them more scalably. So if I just have this actuator, let's first talk about key requirements to achieving flight. So let's not worry about the mathematical equations, but just keep in mind of the key ideas. To fly a robot, you have to satisfy a few requirements. First, you have to generate a lift force that's heavier, that's larger than the weight of the robot. And while you're generating the lift force, inevitably, you're also generating a drag force, so that the block force of your actuator has to somehow fight against the drag force through a transmission ratio. And finally, you want to match the resonant property of your robot to the resonant property of your actuator. What I really focus on today is I want to talk about the requirement on the bandwidth, the free displacement, and also the block force of the soft actuator. So first, let's talk about the bandwidth of the actuator. We model the actuator as a series RC circuit. So we measure the electrical property and realize the RC time constant is on the order of 0.2 milliseconds, which translates to a RC frequency of 5 kilohertz. So the bandwidth of the actuator is not limited by the electrical property, but rather by the mechanical property. So we spend a lot of time trying to choose elastomers of low viscoelasticity and optimizing the geometry of the soft actuator so we can generate a resonant frequency that's as high as possible. In the end, we are able to target something on the order of 500 Hertz. Now let's talk about block force. To measure the block force of the actuator, we mount this actuator under a force sensor. And then we drive this actuator with a purely sinusoidal voltage signal. And then we can measure the instantaneous force profile. We take the 0 to peak force as the block force. And then we vary the driving frequency and also the driving amplitude so we can map out the behavior of the actuator. As you can see on that plot, this 0.1 gram actuator can generate a maximum block force that's on the order of 0.2 Newton. And after we know the behavior of this actuator, we can also measure the free displacement. So again, we place this actuator under a laser vibrometer. We drive it with a purely sinusoidal signal. And we measure the peak-to-peak motion as the free displacement. And then again, we vary the driving frequency and amplitude so we can map out the behavior of this actuator. You can see from this plot that the resonant frequency of the actuator is on the order of 500 Hertz. So now, if I multiply the block force and the free displacement, I can estimate the energy density of the actuator, or I can estimate the power density of the actuator. It's actually a quite important takeaway here in that based on the analysis we done a couple of slides before, we reasoned that as long as a actuator has a bandwidth that's higher than 200 watt per kilogram, it is possible to achieve flight. And in this case, as you can see, our soft actuator has a much, much higher power density, which really implies that flight is possible. So with that, we installed the soft actuator into our robot. And in this particular video, the robot is flapping its wings at 280 hertz, which is even faster than the state-of-the-art rigid robot. And just by looking at that video, having sort of looked through thousands of flapping videos, we know that we are generating enough lift forces. So about 4 years ago, we demonstrated the first lift-off of a flapping wing robot. You can see the artificial muscle in the center are really behaving like true muscles. They're elongating and contracting. I would say that this is a very exciting moment for soft roboticists, but it's not very exciting for aero roboticists. This robot is flipping over in 0.1 seconds, intrinsically unstable, so it's really not very useful yet. Our main task is to stabilize this robot. So to stabilize it, we put two units together. And if I can somehow induce a yaw torque, that is, try to teach the robot to rotate relative to its body z-axis, then effectively the robot is behaving as a spinning top. And I can use that precession to stabilize the robot. Of course, to prove stability, we have to look at the relative contribution between the moment of inertia tensor and the yaw torque. But just skipping over the mathematical proof, let me show you that in both simulation and experiment, we've been able to show this robot is passively upright stable, and it can fly upward at a speed about 30 centimeters per second. This is impressive because there is no sensing or any feedback control involved. And I would argue this is very important for tiny scale systems lacking the ability to do sensing at a high frequency. So far I've shown you that soft robot can take off. They can be passively upright stable. The key question for soft robotics is, are soft robots controllable at a high frequency? So our lab has spent the past 4 years working on flight controllers. And let me show you something we have been able to do about 2 years ago. So this is a 20-second hovering demonstration showing in real time. Okay, so this is one of the longest hovering flights that's been done about 2 years ago among any of the sub-gram aero robot. And as you can see, this robot is really quite stable. It looks like it's just staying at a fixed point very stably. And if you look at the attitude error or the position error, the maximum attitude error is about 2 degrees within this 20-second flight, and the position error is about 1 centimeter. And our lab is continuing to push the endurance of the robot. So as of 2 years ago, we can get to 20 seconds. As of last year, we can get to 40 seconds. And hopefully, by the end of this year, we can push it to be on the order of 100 seconds or so. But there is one key shortcoming, which is that although we have position control, we don't have heading angle control. So when the robot is flying, it's sort of just passively yawing. Imagine in the future, I want to control the robot to stare at something, right? That would be very challenging. So to solve this, we propose a new configuration in which we just slightly tilt the robot so that we can use a component of the lift force to generate yaw control torque. And again, let me skip over the details of the controller implementation and say that now we can track the yaw angle quite well. So the robot turns left, and then it's commanded to turn right, and then it turns forward, and then it lands. So there's still a little bit of coupling, meaning that when the robot turns, we still have a little bit of coupling in the position error. But I would argue that just suffering a couple of centimeters of position accuracy for a fairly good attitude heading angle control is reasonable. And until very recently, we started to collaborate with Professor Jonathan Howe's team. We started to implement a model predictive controller on our robot. So the robot now can track trajectories quite well. And more than that, we can track aggressive trajectories, such as a somersault. So I'll say more about that later on in this talk. So hopefully, so far, I've convinced you that indeed, soft robot can fly, and they can fly just as well as the state-of-the-art rigid robot at the micro scale. But the more interesting question is, what are unique flight capabilities we can demonstrate? Now, the first come in mind is that soft actuators are robust. So now I can repeatedly run a wing into an obstacle, and the actuator sees no damage. And I can push this further. I can try to damage the robot by putting a lot of needles into the actuator or even cut up the wings. And also, because I can now be very harsh to the actuator, I can send in very aggressive control signals. How about turning the actuator on and off in 5 milliseconds so I can do a somersault? And more than that, because we make the actuator in-house, how about putting electroluminescent particles in the actuator so it can shine out light when it flies? So let me show you off this. First, when the robot is flying, now we can gently push down the robot, and the robot can return to the hovering set point. Now, this is really not very impressive. I think most quad rotors can do this as well. But I think what starts to get interesting is if I start to hit the actuators of the robot, or more interestingly, hitting the wings of the robot. You can see that because of its low inertia, the robot is really resilient against collisions. Imagine hitting the propellers of a quadrotor when it's flying, right? That's not going to turn very well. And in fact, what you can do is you can try to hit the robot really hard so that the robot cannot recover. And because of its low inertia, it simply bounces on the floor and returns to the hovering set point. Again, something very challenging to do for larger scale robot. And pushing this a little bit further, right, we are also interested in studying how the robot fails. The most common mode of failure in most cases is the loss of a wing, right? Sometimes the wing hinge is torn and instantaneously the robot loses balance and crashes. Well, if you think about how fragile this robot is compared to real bees in nature, the animals are much, much better. The wings of bees can be fairly worn out, and they're still retaining very good flight capabilities. And there are a class of, or a community of colleagues who are studying how beetle can fly, and they put electrode into the flight muscle of those beetles, and the beetle can still maintain a level of very good flight capability. So the question we want to ask is that can we enable a similar level of resilience in our robot? Specifically, can we teach our robot to fly near a cactus, right, or even putting needles through the robot? So we identify 3 types of things we can do to the robot. First, we can put a lot of needles through the actuators. Second, we can cut up large areas of the wing off from the robot. Or even worse, we can try to hit a hole in the soft actuator. And hopefully, the robot can still maintain their flight capability. On a higher level, dielectric elastomer actuators can be modeled as a soft capacitor. It's just consisted of an elastomer layer that's sandwiched by 2 compliant electrodes. So what's going to happen when I use a needle to pierce through the actuator is that I'm going to generate a path to create an electrical short. And to get rid of that shorted path, what we do is we send in a high voltage, and that high voltage will generate a lot of heat, which will tend to electrically isolate that defect from the bulk electrode. And then once that defect is isolated, the actuator can be functional again. This self-clearing method is very robust in the sense that there's no additional repairing needed. All you need to do is to send in a high voltage, and in some sense, the actuator is able to reheal itself. This process is so robust, in fact, that my student has been able to put tens or even up to 100 needles through this actuator, to the extent that in the end, they stopped not because the actuator failed, but because there's no more space to put in needles. So let me show you how this works for a real robot. We mount this robot on a lift-off stand just to demonstrate it has sufficient power to lift off. Okay, so without any damage, of course, the robot can lift off. And then what the student does is that they will come in with a tweezer. They will puncture the actuator. Okay? Now the actuator is damaged, so the robot cannot fly anymore. So we have to perform self-clearing. And all we need to do is to, again, just command a high voltage. And as you can see, the current response here really are signaling we are generating heat to burn off the defects. Once we clear the damage, then the robot can fly again. And this process is highly repeatable. So we can just keep putting more and more needles to the robot until really it's very hard to put more needles into the actuator. And after being poked 10 times, the robot still retains a level of power density that is sufficient for enabling takeoff flight. Okay, so this set of experiments really convinced us that the actuator is so robust and has such a high level of power density that it's able to retain this flight capability after it has been damaged. But now, let's now think about controllability. In the next experiment, what we do is that we try to first fly a particular robot for about 12 seconds. This is a healthy robot. It's perfectly in shape right now. After you finish this flight, the student will come in and poke the actuator of this robot with a needle. And as you can see, it looks like a quite painful process. It's not easy to put this needle into this actuator. And once we put this needle into the actuator, we would again need to perform self-clearing, which is again just to send in a high voltage. So very slowly, the defects around this needle is being cleared. And once that's done, we can do a very short flight on the order of 3 seconds just to convince ourselves that the actuator is still functional and the flight capability of this robot is unimpacted, right? Once we've done this 3-second short flight, we are convinced that the flight capability of this robot is not impacted, and then we can fly the robot for much longer time. Again, in this case, 12 seconds, just to demonstrate that the flight capability is not impacted. Okay? So now I've shown you that this robot can survive piercing damages, but let's think about something more extreme. How about if I puncture big holes in the actuator to the extent that I really expose the air surrounding it? And what's going to happen by sending a high voltage is literally you're going to set up a fire in the actuator, right? And once you set up those big fires, you set up a huge defect, and the actuator is no longer functional. So how do we recover this actuator? Well, we come up with a method in which we called laser-assisted surgery. The idea is that we are trying to use a diode pulse laser to cut across this defect so we can encircle this defect. Essentially, the laser is trying to create a minor damage that isolates the major damage. And then I'm going to command self-clearing again, which will isolate the laser-assisted cut. And because now the minor defect is isolated, and it isolates the major defect is now also isolated. So let me show you how it works. We burn a big hole in the actuator, and after performing this laser-assisted surgery, we can show the robot is operational again. So in the end, we have been able to come up with one robot that suffers 3 types of damages. One of the actuator has been pierced by 10 times. One of the wing is being cut off by 20% near its wing root. And also one of the actuators suffers a big hole that's burned in the center. And in this case, we do need to retune the flight controller, which means that we need to figure out the reduction in forces and retune our flight parameters. But after that, we can demonstrate an equally well controlled hovering flight. And I would argue that this video demonstrates a level of flight resilience that's really unprecedented among existing rigid flying robots. And now let me change here to talk about agile locomotion. At least in simulation, we show that our robot can do a very quick somersault. And what's interesting about somersault demonstration in a small-scale robot is that because it has very low inertia, the speed of somersault is really very high. In simulation, we show that a somersault can be done within 0.15 seconds. This is faster than any of the existing aero robots. And now let me show you what's going to happen in real time. Okay? So in real time, you're going to see this robot takes off and hover, and then try to do a somersault very quickly, and then it tries to recover to the hovering set point. Now let me play the same somersault video in a slowdown time. In this case, the robot first hovers around the set point for 2 seconds, and then it accelerates upwards, tries to make a somersault, and then try to recover its attitude, but it couldn't really recover, so it hits the floor and bounces back and eventually returns to the hovering set point. One of the most challenging part in this demo was trying to recover the attitude after the somersault. And in this video, which is something we've done about 2 years ago, everything was done by a PD controller. So we have split the flight into 5 phases: takeoff and hover, ascent, trying to do a somersault open loop, try to recover, and eventually return to the hovering set point. Something that we don't have a very good model of is what's the aerodynamic model when the bee is falling. And again, in collaboration with Professor Johnson Hao, we recently have a much improved force mapping. So very recently, the robot is able to do a somersault without hitting the floor. I hope I'll have more to say about this in the next few months. So in summary, we can perform a somersault, and we can perform 5 somersaults straight without seeing much change of the performance in the robot. And that again shows how resilient this robot is at this very small scale. Now let me change gear again and talk about bio-inspired functions. In this case, we take inspirations from fireflies. Fireflies are quite amazing animals. When they fly, they shine out light, and they use the light emission to communicate. And since we can make our soft actuators in-house, we can embed electroluminescent particles in the actuator so that when the wing flies, the robot can shine out different colored or pattern light depending on the type of particles we put into it. And let me show you how it works. When the robot flies, we can take a couple of iPhones and then film the flight of this robot as each of the actuator lights up. So it looks pretty cool, but in addition to being looking cool, what we are really after is the ability to replace a very expensive motion tracking system. Traditionally, to fly this robot, we have to use an infrared motion tracking system that sends infrared radiation that are then bounced back by those Vicon markers. Now, if the actuator can emit light, then the actuator itself can be used as active markers, so that in contrast to using infrared-based tracking systems, we can probably just use a couple of cheap cameras and do motion tracking. So we've implemented very simple computer vision algorithms, and we have compared our tracking result with the state-of-the-art Vicon motion tracking system. Have we been able to show that our tracking result is quite good? We have an error on the order of a couple of millimeters and about 2 to 3 degrees. So again, we are not very good computer scientists. Our code is not very efficient. So if some of you are working on computer vision, please reach out, and we'd love to collaborate and implement this algorithm in real time. Another thing we are looking into is trying to fly a large number of micro-scale robots. Our student is interested in exploring 3D printing method, so we can replace the airframe and structural component, and in such a way that we can make them more scalably and consistently. About a few months ago, for the first time, we can fly 2 micro robots together. And in this case, while they're flying, they're trying to carry a small payload. Now, again, we are not a planning and control lab. We don't do very fancy control algorithms. So really, the 2 robots are not knowing that they're collaborating and carrying a payload. And in fact, my student had so much fun that when he was flying those 2 robots, he tried to put our lab name on this object. But I hope what I can convince you is this is really interesting. This is really moving towards swarm flight. What we are really interested in the next few months is teaching the robot to do some pollination demonstration, teaching 2 of them perhaps to land on flowers, take off, and land on other flowers. Again, I hope I'll have more to say about this in the next few more months. So in summary, we have created unique soft aerial robot that can demonstrate multiple things. This robot is robust against collisions. It's fairly agile, considering it's only 3 to 4 centimeters. Its top speed now exceeds 1 meter per second. And more than that, it can demonstrate unique functions such as light emission. And within sub-gram aerial robot, it can now fly in a small swarm. So in the last 4 or 5 minutes, I want to address the question about what are we trying to do in the longer term. I would say that at this scale, one of the biggest challenge is to achieve power autonomy. And we are very much aware of the performance gap between soft robot and the state-of-the-art rigid robot. So back in 2019, there was really a foundational paper published in Nature on piezoelectric-driven power autonomous aerial robot. And if we compare the key performance metric of soft actuators with rigid actuators in terms of power density, robot lift-to-weight ratio, actuation voltage, and efficiency, you can see the soft actuators was way worse. But I also want to say that because we make everything in-house, we know what to improve. as of 2 years ago, we have been able to significantly improve the power density of the actuator, and as a consequence, also improving the lift-to-weight ratio of this actuator. But we also realized that the actuation voltage is significantly higher than 200 volt, and that would really make making a sub-gram power electronic circuit difficult. So with the requirement of trying to achieve power autonomy, we set out to reduce the actuation voltage. On a higher level, the dielectric elastomer actuator, again, is composed of a soft capacitor. To reduce the actuation voltage, theoretically at least, all you need to do is to reduce the layer thickness. So we use a spin coating method, and intuitively, if you just spin coat faster and faster, you can reduce the layer thickness, and hopefully you can reduce the operating voltage. Again, without going into all the details, let me just say that as of 2 years ago, we are able to come up with an actuator that has a similar size compared to the previous actuator, but has much larger number of layers, while each layer has a much thinner thickness. And as a consequence, we can achieve similar block force and free displacement at a much lower driving voltage. In comparison, what we have been able to achieve at 2 kilovolt, now we require about 600 volt to achieve. And that will make the life of making power electronic circuit a lot easier. And as of 2 weeks ago, my students have been able to further reduce this voltage to on the order of 400 volt. So we are really spending a lot of effort trying to reduce the operating voltage, so putting on onboard circuitry is feasible. So with that, we developed the first tap inductor boost circuit for our robot. This is still a very simple circuit topology. We make our circuit in-house, we populate that with commercial component, and then we put that tiny circuit on top of our robot. So this robot weighs about 160 milligrams while carrying a 130 milligram circuit. Now, I want to say that we are still far away from power autonomy. We cannot carry our own battery yet. This circuit still requires an input of 7.7 volt DC, and then it will convert a DC low voltage input into a 600 volt and 400 hertz AC output, and you can use that to drive the robot. We can achieve quite good flapping kinematics. And finally, the student is able to demonstrate takeoff while the robot is powered by this at scale tiny boost circuit. In the first example, the circuit is off-board, and we are trying to put a 120 milligram payload to mimic the takeoff condition. In the second experiment, what we did is we mount this circuit on board, and you can see the robot can still generate sufficient force to do liftoff. But of course, this is still very early stage work. We cannot put a battery on board yet, and we also don't have onboard computation. So this is really some of the key challenges we are trying to work on now in our lab. So finally, I just want to say that we are also working on new configurations. I'm very interested in the aerodynamics of wing-wing interactions. In collaboration with Professor Rob Shepard at Cornell, we are working on combustion-powered microflying robot. I'm very interested in trying to fly a large number of microrobots together. And we are also thinking about multimodal locomotion. So hopefully one day those robots can land on flowers or perch on tree branches. With that, let me zoom out and say that our longer-term vision, again, is to deploy a large number of micro-scale robots in a realistic environment. We are still very far from it, but hopefully I've convinced you that we are addressing key challenges in actuation, control, and planning. I would argue that the next 10 to 15 years will be a very exciting time for people working in this area. So with that, I want to thank my prior advisors, Professor Rob Wu, David Clark, and Jane Wang, my collaborators. But most importantly, a lot of the work that I presented today are really led by my students in my lab. We are still a very small lab in MIT, but we are making very fast progress in the area of microrobotics. I want to stop here and take questions. Thank you.
Questions? Yes.
I was just wondering, if the power is off the B, Why is it only able to last 40 seconds or so? What is the limiting factor for lasting longer?
So that's a very good question. Right now, the limiting factor of the flight time is the lifetime of the wing hinge. So the wing hinge, I think now has a lifetime on the order of 100 seconds or so. After 100 seconds, you have to replace the wing hinge and change to something new. And in fact, in the failure videos that I've shown, is all of the cases while it's flying, the wing just flies off. The actuator lifetime is very long. It's on the order of an hour or so. So again, we are thinking about a lot of things to improve the lifetime of the hinge right now. But that's a very good question. Thank you.
Thank you.
I was just curious if you change your flight mode to like propellers, for example, if we made quadrotors at that scale, would it simply not be able to fly?
So that's a very good question. The short answer is I think it will be able to fly. What's very challenging at this scale is making very tiny motors. If you shrink down the size of motors, the torque density shrinks, so that I would argue anything that's less than 0.5 gram is very difficult to make out of the motors. And then if you compare the aerodynamic efficiency of propellers as in comparison to flapping wings, propellers are more efficient aerodynamically, but flapping wing flight can generate more forces per area at the same velocity. So in some sense, it's also harder to shrink down the scale of quadrotors at this scale.
Thank you.
Yep.
That was amazing, Kevin. Thank you for that. So you showed quickly some CFD work.
Yep.
I'm just curious, did you learn anything in the CFD that changed your design? Did that transition, or what were you trying to get out of the CFD work?
So that's a very good question. Yeah. The CFD helps us to understand the flapping wing kinematics, so we use that to optimize the shape of the wing design and to optimize the wing hinge design, specifically determining an optimal stiffness. One thing I didn't have a lot of time to go into is that, again, this is a very complicated physics question. We are studying the passive fluid structural interaction. We don't have full degrees of control of the wing pitch motion. So you really both have to optimize the wing shape and also the wing hinge stiffness, so we can get to something we call negative phase shift, in which it's both more efficient and also generating a larger lift-to-weight ratio. And that requires us to look at the vorticity contour and the isovorticity contour and also the pressure profile on the wing surface. So in some sense, the suite of experimental tools, the particle image velocimetry experiment, and the computational tools are not useful for control, but useful for the design of those robots.
So Kevin, maybe I'll ask one question, then I'll pass it on to you. So do you have any suggestions for people who are working from not on micro robots but macro robots? Is there something we can learn from micro robots that we can apply to larger scale robots?
So I would say, again, the interesting thing to me about microrobot is, again, inertia is less important and surface effect become a lot more important. So what we don't have a lot of expertise and are very interested in terms of collaboration is thinking about swarm algorithms. When I'm thinking about fly a swarm of microrobot, collision is no longer constrained. Maybe you can use collision to do something, right? Or interaction with obstacles, fly into walls or land on flowers. So there are a lot of new things in terms of swarm behavior that we can think about. Again, we are not working on algorithms or planning, so that's really something we think, planning people or swarm behavior people that and us can collaborate on.
Thanks so much for a great talk. This may be more nitty-gritty than most people want, but I'm curious, with the wing failure, what the material you're using for the hinges is and what the failure mode is, whether that's material failure or perhaps an interface failure or something else.
So that's a very good question. So when the wing hinge fails, it usually turns along the wing hinge. For a very long time, we thought that is because of the fatigue of the capital material that we are using. Now, having talked to Xuanhe Zhao in the Mackey department, Professor Xuanhe Zhao, he thinks it's not a fatigue problem. He thinks it's a torsion problem. And I think he's more or less right. When we change the relative flapping phase, we do see a large change of the lifetime. So I think, in short, again, we don't have a lot of expertise in that area. Initially, we saw this a fatigue problem. Now we think it's much more complicated problem than fatigue.
Thank you.
Yep.
So I remember you had talked about the weight of the power electronics and trying to bring that down. Do you have a sense of what the weight for battery capacity would be and how much flight time you could get if the mechanical issues weren't an issue?
So that's a very good question. The smallest battery that we can buy about 0.3 grams. So we are trying to, for example, build a robot that's on the order of a gram or so that can have on the order of 2 grams of payload. So we can carry a small battery and a small boost circuit. We are not so much limited theoretically in terms of flight time by the amount of energy a battery can contain. Battery has way more energy than we need to fly. What's really limiting is the amount of power that we can source from the battery. So I was talking with our collaborators, I was trying to say that we either don't have any flight, or when we can fly using a battery, we can have tens of seconds or hundreds of seconds of flight. So our real concern is about sourcing large amount of power from the battery, not so much how much energy the battery has.
All right, thanks.
Yep.
Hi, thank you for the talk. I'm curious, throughout the soft actuator portion of the talk, we saw different variations of the robot. I think one had one soft actuator, 2 actuators, and then 4 actuators. Do you view this as a progression, or is it something that you might use one robot in one situation and a different robot in another situation?
So that's also a very great question, right? So in some sense, when we submit papers, sometimes the feedback we got is, the robot works great, but it looks so ugly. and partly the reason is this. I would say that one unit is not too ugly, but it's really difficult to control. If you look at the soft actuator actuation as a control problem, it's nowhere near to be linear in comparison to the piezoelectric actuator. So when we fly a piezoelectric actuator-driven robot, we can inject higher order harmonics to generate control torque. Whereas in the soft actuator, we are literally just driving it harder or less hard and use 4 units to fly like a quad rotor. So in some sense, if, again, some of you are interested in nonlinear dynamics, generating nonlinear controllers, so we can somehow inject nonlinear signals and get the kind of output strain that we want, I think there is a potentially we can build 2-winged soft actuated robot that can fly very well. So again, that's, I would say, a limitation in the kind of control algorithm or modeling that we have, not so much a fundamental limit that we have to fly with 4 actuators and 8 wings.
Okay, thank you.
Any more questions?
Thanks for the talk, Kevin. I'm curious if further miniaturization is possible, and if we're limited by the manufacturing techniques, or and what would be gained from making 1/4 of the size of the current B.
So that's a very good question. Actually, Suhan is in the process of shrinking down the size of the B. I think hopefully in a couple of months we are going to fly something that's not. So this robot is about 600 milligrams with the 4 unit. Hopefully in a couple of months we can fly something that's on the order of 300 milligrams. Now, I would say we don't have really a limit for shrinking, unless you want to shrink it by hundreds of times. But considering the challenge in power autonomy, which is something that we want to focus on now, there is a fabrication difficulty for tiny scale circuit and batteries. So what we are aiming for is, again, creating something that has a payload on the order of 1 to 2 grams, so we can put down the batteries and the circuit. So I would say our top priority is not in shrinking down the size of the robot, but rather build a platform that's large enough to carry the onboard batteries and sensors.
Thank you.
Yep, thank you.
Great. So let's thank Kevin once more for the amazing talk.
Thank you.